The 17th of January commemorates the birth of Benjamin Franklin, a key figure of science and politics. His influence has been so significant that he even gives name to a crater on the lunar surface, visible from Earth. Today we will explore a fascinating mystery related to the moon, its hidden face. Before continuing, I invite you to subscribe to our channel and give like to this video, so you can be aware of more interesting content about science and the universe. For decades, scientists have observed a profound asymmetry between both sides of the moon. The visible hemisphere is dark and smooth, while the hidden one is clearer and full of craters. This difference has generated many theories, but none have explained the phenomenon completely, until now. A recent study, published in the journal Proceedings of the National Academy of Sciences, offers a new explanation. Based on isotopic iron and potassium data obtained by the Chinese Chang'e 6 mission, this work solves an old lunar enigma and reveals the massive impact that modified the lunar mantle. The differences between the two sides of the moon are not only superficial. The hidden face has a thicker crust and less volcanic activity. Since the Soviet mission Luna 3 in 1959, attempts have been made to understand this asymmetry without conclusive results. Now, Tian's study and his team provide clarity. The study focuses on samples collected by the Chang'e 6 mission at the South Pole-Aitken, one of the largest impact basins of the solar system. The fragments analyzed revealed that the isotopes of potassium and iron are heavier than those of the samples of the Apollo and Chang'e 5 missions. This isotopic difference indicates that the mantle of the moon underwent a unique process, resulting from a gigantic impact. This discovery is crucial to understanding how violent events in lunar history have shaped its inner structure. The isotopes are versions of a chemical element with different mass. In the case of the moon, the massive impact caused the evaporation of lighter isotopes, leaving a chemical footprint on the rocks. This allows tracking extreme events that occurred billions of years ago. The proposed model suggests that the impact generated sufficient heat to vaporize volatile elements. This loss of potassium by evaporation explains the isotopic signatures observed in the Chang'e 6 samples and confirms that the impacts altered the composition of the lunar mantle. This study not only clarifies the origin of differences on the moon, but also has implications for understanding other planetary bodies. Impacts have been common in the history of the solar system, and knowing its effect on the moon helps interpret data from other missions. Finally, the conclusion is clear. The impact that formed the South Pole-Aitken Basin not only transformed the lunar surface, but left a permanent mark inside it. This allows us to better understand the evolution of our satellite and other celestial bodies.